Good afternoon, ladies and gentlemen. How are we doing? It's Tuesday. It's 2 o'clock. It's chemistry time. Oh, Dexter's on the move. All right, bud. You want to come and say hello to everyone? Say hello to the year 12s? No? Back in your basket? Come up here, mate. Come and say hello. How are we doing? Hey, Miss C. Hey, Dennis. Hey, Hadia. Whoa, here we go. You say hello, bud? You say hello? Who says? Who says? It's the chemistry dog. What? You look a bit scared, mate. What's going on? Right. Down you go, mate. We got to do some Equilibria and KC and Le Chatelier's and all that jazz. How are we doing? Everyone looks okay. Who have we got in the house? Massey, Dennis, Hadia, Benyon, Megan, Tabo. I do apologize. Charisma, Christine. Hey, we've got a few new names in here today. Molly, how are we all doing? Lily, great. Kerry, fantastic. Loads of new people. Just give me a quick hands up or a quick I'm a newbie if you are a newbie, which is absolutely awesome. You are absolutely welcome. Welcome. Yeah, so these live sessions have been going just for over a week now. I think they're going okay. I think we're helping people finish their specifications and making sure that, you know, you're primed and ready for year 2, to be honest with you. So yeah, that's what we're doing this week. And we're going to crack on. We're going to crack on with some Le Chatelier's. We're going to crack on with some Equilibria and some KC as well. So this is just like an overview. It's like a whistle-stop tour. I'm going to give you like a best of in terms of my explanations as to how things work, so on and so forth. Yeah, obviously, any questions as we're going along, just stick them in the chat, and we'll cross those bridges as we get to them. So first up, let's have a quick overview, shall we? So let's just get my iPad up and running. And what we should be seeing now is my blank screen. Okay. Grace, how are we doing? Chem gang. Yeah, I like that. We like the Chem gang. It sounds like we should be singing that, but there we go. Right. Okay. So let's get this up first and foremost. So in terms of Equilibria, let's make a better start than that, shall we? So Equilibria. Essentially, between all the exam boards, it's pretty standardized as to what everybody needs to know. All right. So in terms of Equilibria, there are some major areas that we need to cover. Okay. So obviously dynamic equilibrium is one. So what is that? We need to be able to describe and understand what one is. We need to look at Le Chatelier's. All right. And we also need to look at maybe some industrial examples, because they are by far the most common types of question you get, where they based those questions on industrial examples. And then last but not least, we need to look at some KC, which is the quantifiable side of this. Okay, so you know, for most part, dynamic equilibrium, Le Chatelier's, and so on and so forth, we like, oh well, it shifts to the left, it shifts to the right, whatever. But of course, we need to put some numbers to it. Okay, KP is something that you get to in year 2, and that's a walk in the park. If you can do KC, you can do KP with your eyes shut. We may even get to the point where we start talking about that today. So I'm going to give you guys just maybe next 30 seconds. What I'd like you to do, please, is if somebody said, what is a dynamic equilibrium? What would you say? So if somebody asked you, what is a dynamic equilibrium? Will you see it in an exam paper, or your nan asked you? I don't mind. But what is a dynamic equilibrium? Put your best answer in the chat for me, and we'll kind of run through those and see if we can pick out maybe one that's nailed down. Dennis says it's constantly changing. Changing isn't a word I would use in terms of describing what a dynamic equilibrium is. So Hadia, when the rate of the forward reaction is equal to the rate of the reverse reaction, equilibrium keeps changing constantly. Forward reaction is equal to the backward reaction from Megan. A state of reaction where the forward and backward reactions are happening at the same time and at the same rate. That's pretty good. Hi, Emily. Forward reaction is equivalent to the backward reaction. Forward and backwards reaction happen at the same rate. The rate of the forward is equal to the rate of the backward. Equal products reactants in a closed system. Equilibrium that occurs in a closed system where the concentration of reactants and products is constant. Good. When products and reactants remain constant. Okay, perfect. Right. So between you all, you've nailed it. Some people have put some things in that maybe they shouldn't. Some people have left things out that maybe they shouldn't. Okay, but we'll nail this down. So a dynamic equilibrium. Okay, what we don't need to do necessarily is mention a closed system. So this is where the rate of the forward reaction, I'm just being simple there, the rate of the forward reaction equals the rate of the reverse reaction. Okay. Therefore, the concentrations or amounts, if you like, of reactants and products remains constant. Okay. So in a dynamic equilibrium, you have, and most of you said this, which is absolutely bob on, the rate of the forward reaction equals the rate of the reverse reaction. And as such, okay, the products are being turned into reactants as quickly as the reactants are being turned into products. So what you will see is no change in concentration. Okay, so let's say in an equilibrium where A plus B gives you C and D, okay, let's say the concentration of these are 1, 1.5, 2, and 0.5. I don't know, just making this up. You will see those concentrations perfectly like level, okay? They will not change. A is reacting with B and turning into C and D the whole time, but that's happening in exactly the same, at exactly the same rate in the reverse reaction as well. So just think of it like the actual atoms, the physical atoms don't stay as A and B. They're getting turned into C and D. But just as it's like one in, one out. Okay, think of it that way. That's what a dynamic equilibrium is. So it's reached this point of equilibrium whereby all the concentrations of reactants and products remain constant, but it is reacting consistently. Okay, it's continuing to react forwards and backwards. Now, this happens, okay, naturally. All right. So let's say if I was to have a closed system, let's say if I was to have a system whereby, I'm going to write this out again, actually, A and B get put into a closed system. And we know A and B react together in a dynamic equilibrium. So let's say initially, and I'm going to use this in a bit, initially I mix 1 mole of A with 1.5 moles of B. So how many moles of products have we got initially, ladies and gentlemen? So in a question, a scientist or a chemist put 1 mole of A and 1.5 moles of B into a sealed container. Okay, I'm going to go with SR and Miss C. There is 0. Initially, there's 0 of C and D. So initially, if a chemist put 1 mole of A and 1.5 moles of B into a sealed container, what's the initial concentrations of C and D? Nothing. Okay, there's none of those present whatsoever. However, if you leave that, okay, over time, then A and B will, of course, react to make C and D. Okay, so at equilibrium, okay, so if there is time in between there, then at equilibrium, it may be that we get 0.5 of this, 1.0 of that, and we make 0.5 and 0.5. Okay, so there's no reaction initially. Okay, but then you leave it over time, and then an equilibrium is established. Okay, so initially A and B are reacting to make C and D, and think of it like a seesaw. Okay, so at the moment you've got loads of A and B and nothing of C and D down here. Okay, then over time it does this. C and D are being made, but then it reaches the point where the forward and reverse reactions level out and you get that equilibrium and they stay. So the forward reaction and the backward reaction are still happening, but you've reached this point where it's balanced. Okay. Now, of course, what happens, okay, with every single reaction is that an equilibrium is established at a different point, okay, at a different point. So let's say sometimes it can be perfectly in the middle. I'm going to use a different color for this. So sometimes an equilibrium can lie perfectly in the middle, okay? Sometimes an equilibrium can lie quite far to the left-hand side. So in other words, you might end up with, still a lot of your reactants are there, okay? And you get most of your molecules are as A and B. So that's where we say the equilibrium lies to the left, where you've got more of A and B than you have of C and D. But then equally, the opposite can occur, whereby the equilibrium lies quite far to the right-hand side and you have more products than you do reactants, okay? So an equilibrium, as far as we're concerned right now, qualitatively can lie in the middle. It can lie to the left-hand side or it can lie to the right-hand side, okay? So let's say we're in the business of making C. C's a wonder drug, okay? So we're in the business, we're in industry, we want to make loads of C. What would we prefer? Would we prefer the equilibrium to be lying to the left-hand side, in the middle, or to the right-hand side? As an industrial chemist, where would you want that to lie? Absolutely. We want more of C, okay? So we want it to the right-hand side. So naturally, this equilibrium could lie to the left-hand side. It's like, this is the only way to make C, right? This is the only way to make C. It could naturally lie to the left-hand side. What we want to do is shift it over to the right-hand side so we get more of this product. We don't want C turning back into A and B again. We want our product, right? So we ideally want this equilibrium to lie to the right-hand side. So naturally, okay, at standard conditions, every equilibrium basically lies to the left, to the middle, or to the right to varying degrees, okay? So it's like a proper scale. But the thing is, what we can do, of course, is influence that position of the equilibrium, all right? So maybe it doesn't lie naturally to the right, but what we can do is kind of force it that way. And that's where Le Chatelier's principle comes in. That's where Le Chatelier's principle comes in. So let's stick to A, B, C, and D. So A plus B makes C and D. Okay. Now, where shall we start? I tell you what, I would like each one of you to write down one condition that could affect the position of the equilibrium, please. Just one, and between us all, we'll get them. Okay, so what conditions could actually affect the position of equilibrium? Cool. Right, so we're straight in there. We have got temperature, pressure. Yeah, absolutely. Concentration. Yeah. Any more for any more? Ruhab, not a catalyst. Basically, we've got all three of them. Okay, these are our big three here: temperature, pressure, and concentration. Okay, surface area, no, not for surface area. Okay, so we've got three conditions that we can change in order to influence our position of equilibrium, and this is where Le Chatelier's principle comes in. So just like we did before, what I'd like you guys to do in the next 30 seconds, and I'm going to give you that time, is to type out Le Chatelier's principle. What is Le Chatelier's principle? Give me your best kind of definition, if you like, of Le Chatelier's principle. All right, Salma, if you've got a question, you can just put it in the chat, mate. That's no problem. So what is your best definition of Le Chatelier's principle? Okay, so I'm going to read as many of these out as I can. Equilibrium shifts to counteract change. I think we can probably delve a little bit deeper than that, Benyon. Equilibrium will shift to oppose a change. Yes, that's true. Equilibrium will shift to counteract a change. Same thing. If the conditions in equilibrium change, the equilibrium shifts to oppose that change in a closed system. I like that, Christine. That's more like it. And the condition of a reaction in a closed system of change, equilibrium shift to oppose a change. Shalane, yeah. Louis, principal statement. Sorry, I'm trying to read them all. Condition is changed, the system counteracts the change to favor its reaction. Nearly. When there's a change in the system, equilibrium counteracts the change. A lot of people use the word counteract here. When there's a change in the system will counteract the change by shifting to oppose the change. The position of equilibrium will shift to minimize the change in the system. That's a different one. If a change is made to conditions of equilibrium position and opposes to the change. Okay, right. Lots to take in there. For me personally, okay, and you're going to see different ones in different places. For me, the closest to my personal kind of, I don't know, say favorite, but the one I would use in an exam is Christine's. Okay, so this is it. So if the conditions of equilibrium in a closed system are changed, the equilibrium will shift to oppose that change. Okay, so we've all kind of got there roundabout, but make sure you really nail down this definition, because you know what Le Chatelier is, it's really handy. I can't remember in the new spec, I don't think they've ever said for 1 mark, state Le Chatelier's principle, not in a new spec, but it's there in your mind and it really, really helps you get to grips with what's actually going on. Okay, so if the conditions of an equilibrium in a closed system are changed, the equilibrium will shift to oppose the change. Now, why is a closed system important? If it's an open system, okay, that means pressure can change, okay, temperature can change, reactants or products could escape, okay, so you need to have them all within a sealed container. That's what a closed system is, a sealed container. That's essentially what it is, okay, and it needs to be that sealed container, because I'm going to give you an analogy in a bit to help you understand that. So let's do these. Let's do these three. Okay, let's talk about these three. So concentration. Okay, let's do this in. Let's do different colors. Okay, so green for concentration. Now we got to think about the only way an equilibrium can shift to oppose a change. Remember, in a dynamic equilibrium, the forward reaction and reverse reaction are happening at the same rate, okay, are happening at the same rate. Now, in order to change the position of the equilibrium, the forward reaction and reverse reaction have to be happening at different rates, okay? So if it was shifting to the right, that means the equilibrium going forward, the reaction going forward must happen faster than the reaction going backwards. Okay, so think of it, we're making more C and D, they're equal, but then this one forces it over this way. So you get more C and D being produced and less A and B until it reaches a new equilibrium. Okay, so what it will do is it will shift to change the concentrations of reactants and products until it reaches a new equilibrium to balance them out. Okay. So does that mean the amount of products reactants can be different? It's just the rate is the same. Yeah, absolutely. Okay, so they'll find a new level. Okay, so think of it this way. When we shift an equilibrium, let's do swapsies. Okay, so I'm being handed, I don't know, a drink. Okay, and I'm handing back a drink. So right now I'm getting a drink, I'm handing a drink back. I'm getting a drink, I'm handing a drink back. So that's a dynamic equilibrium, one in, one out. Yeah. When an equilibrium shifts to find a new balance, okay, so let's say I've got a stock of 5 drinks. They've got a stock of 5 drinks over there. One in, one out, equilibrium, perfectly balanced, okay? But then if it shifts to the right, if it shifts towards me, I get handed 2 drinks and then they get 1. Now all of a sudden, I've got 6 over this side and they've got 4 over that side. So the equilibrium shifted over to my side, but yet we're still going one-on-one. It's just that once they handed me 2 drinks. Does that make sense? I don't know where I'm going with that analogy, but that's kind of what happens. It's like there's a shift. Oh, all of a sudden we made more C and D, but then the equilibrium's reestablished and we're back to the forward rate and the backward rate being equal again. It's just that now most of the atoms and molecules are C and D. Okay, so great. I'm glad that makes sense. Okay, so it's just we're shifting that equilibrium, but then the forward and backward rate they do equal out again, and we remain there. Okay, so we're just tipping the balance. So let's say we've got an equilibrium already established. If I was to increase the concentration of A, now we've upset the balance. Okay, we've put more A in. Now it was at equilibrium. Now remember, what this equilibrium is trying to do is oppose the change. So let's think about this baby steps. I personally have increased the concentration of A. I've put more A in there. What is the equilibrium going to do because I've increased the concentration of A? Directly, don't think about equilibrium for now, but directly, what is the equilibrium going to try and do if I've increased the concentration? You're right. You're right. But I'm thinking more literal. Okay, I'm thinking more literal. The equilibrium will shift to oppose the change. What is opposing the change, ladies and gentlemen? Boom. Rakea. That's what I was after. You guys are not wrong. Those are right. Those are written, you're shifting it to the right. You're absolutely right. But I'm going baby steps here. So if I increase the concentration of A, the equilibrium, what it wants to do, okay, is decrease it again. The opposing the change means bringing that back down. We're bringing down the concentration of A again. It's not happy. I've messed with its chi, right? I've messed with its feng shui and I've increased the concentration of A. So it's going to try and bring it back down again. The only way an equilibrium can do that is by handing those 2 cups of coffee over, right? So it's like, right, I'm going to get rid of you. I'm going to put you over there. So we're back on a balance again. So if I increase the concentration of A, it opposes the change by bringing it down. The only way in which you can decrease the concentration of A in response is to react it with more B to make C and D. And once it's done that and it's reached a new equilibrium, then it's happy again. Okay, it's reached a new equilibrium. So what you'll find is that if you increase the concentration of A and a new equilibrium is established, what's the deal with B then? So I've increased the concentration of A, it's shifted to the right. All of a sudden, are we going to have more B or less B after it's shifted? Good, yeah, less B, because we needed to react some of it with A in order to bring it back down and shift it to the right. Good. Of course, as a consequence, overall, in the equilibrium mixture, we're going to have more C and D. Okay, more C and D. Okay, so that's what happens there if I increase the concentration of A. Now, so that makes it shift to the right, of course. There's probably 3 other things in terms of concentration, 3 changes in concentration that I could make in all that would also shift the equilibrium to the right. What are those? Give me one of those 3 changes, people. You pick one. So there are 3 other changes I could make to concentrations here that would shift it to the right. What are they? Raseb, straight in there. Increasing in B, absolutely. Okay. So to shift it to the right, I could increase the concentration of B, as Raseb said, increase the concentration of A, as I said. What else have we got? Anybody mention that? Oh, yeah, Shalane, decrease C. So we can decrease the concentration of C, absolutely. And Dennis, we can decrease D. And I'm sure other people said that as well. In fact, I know you did. I can see that. Perfect. So shifted to the right, we increase the concentration of reactants, or we decrease the concentration of our products. Of course, the opposite is true, going the other way. So changing concentrations is a really neat trick that industrial chemists use in order to maximize their yield of product. Okay, so for example, a real life example is N2 plus 3H2 gives 2NH3. Now, this is an equilibrium, and it does lie a little bit to the left-hand side. Of course, we want to make ammonia, the Haber process, whatever you want to call it. We want NH3 and lots of it. What we actually do, what the chemists actually do, the industrial chemists actually do, is they continually remove NH3 from the process. Okay, and they do that by cooling it down. They cool it down, hydrogen bonding between ammonia molecules, so it's got a really high boiling point, which means it's got a really high condensing point, so it turns into a liquid at a high temperature. Okay, so what they do is they lower the temperature at one point during the Haber process, okay, at one part of the flow, and then the NH3 comes out as a liquid, whereas these stay as gases and they get pumped around again. So they're constantly taking NH3 out. So what's happening is they're tricking this equilibrium into constantly shifting to the right, trying to redress a balance, okay, and trying to make more NH3 to reach an equilibrium again. This is what I mean by a closed system. If we have an open system and we're constantly removing NH3 like we do in the industrial process, it never reaches an equilibrium. We're constantly just like removing the product and it constantly trying to make it. So that is why a closed system is really, really important, okay? Because if you don't have a closed system, it will never reach equilibrium, okay? Never reach equilibrium. So has anybody got any questions in terms of concentrations? I think this is probably the simplest of all of them, isn't it? Just post them in the chat. If you haven't, then just give me a nope or a thumbs up or a whatever. I don't know. Just use your imagination. Not too much, mind. It's a family show. Sweet. We'll talk about catalysts at the end, Ruhab. Yeah, it's a very good question. Why? So yeah, we'll talk about that at the end. So the Haber process is a dynamic equilibrium, Miss C. Yeah, absolutely. It is a dynamic equilibrium. It is in a closed system, apart from when they are cooling it down and removing the ammonia from the system, in which case they've opened the system, removed the ammonia, and it doesn't reach equilibrium because they just keep taking it out. Okay. So what's next? Let's do pressure. Whoops. Didn't mean to rub that out. So I'll tell you what, I'm on ginger, so we'll go with ginger for pressure. So pressures, very importantly, what do, no, there isn't, Louis. Okay, no other types of equilibrium. There's a dynamic equilibrium, that's it. Okay, so in terms of pressure, this only affects reactants and products that are gases. Okay, hopefully, Aisha. Okay, hopefully. So I'm running through as fast as I can. So pressure, this is the same. If I increase the pressure of A, in fact, no, tell a lie. Let's change this equilibrium slightly and let's do 2C and 3D. Okay. Oh, boom, somebody's already ahead of me. Who's this? Mona. Increasing the pressure in the equilibrium will favor the side with the least number of moles. Good. Okay, so in total here, we've got 2 moles of gas. Over here, we've got 5 moles of gas. Now, if I increase the pressure, okay, so I've increased pressure, literally, remember what I was saying before, baby steps. If I increase the pressure, the equilibrium is going to try and do what? Don't talk about shift. What's literally, if I increase the pressure, the equilibrium is going to try and counteract the change, decrease the pressure. Okay, good. So the equilibrium tries to decrease the pressure. Now, again, it's not a thinking, living, breathing thing. The only thing it can do is shift to the right and shift to the left, favor the forward reaction, favor the reverse reaction. Okay, so it tries to decrease the pressure. The only way it can try and decrease the pressure is by favoring the side with the fewest number of moles. Okay, the reason, the volume of the container is exactly the same. Okay, if you've only got 2 moles of gas present, relatively speaking, then they're going to create less of a pressure. If you've got 5 moles of gas present, they're going to create a higher pressure. Okay, it's like blowing up a balloon. The more moles of gas you've got in a balloon, the higher the pressure. The fewer number of moles of gas you've got in a balloon, the lower the pressure. So that's why it does that. It favors the side with the fewest number of moles. Okay, so if you increase the pressure here, Louis, boom, shifts to the left in this case. Okay, so what you need to say to yourself, it could be an equation whereby they're not all gases, but you just look at the gases. It's only about gases, this. Okay, so it's a case of spot the gas. How many moles of gas have you got on each side? An increase in pressure favors the side with the fewest moles of gas. A decrease in pressure, it's like, well, hang on a minute. I need to get this pressure back up again. So it favors the side with the greatest number of moles of gas and then increases the pressure that way by making more stuff. All right, so that's it. So this links directly to like molar gas volume and things like that. Okay, 1 mole of any gas occupies the same volume at the same temperature and pressure. Okay. Good. So pressure is nice and straightforward. In fact, at this juncture, I am going to very quickly describe to you, and I should have brought one with me. I didn't bring one with me. I've got the wrong drink. But let me just kind of do this with you for a sec. So in terms of pressure and closed system, right? We've all had a bottle of pop before now, a bottle of Coke, something like that. Okay. Interested in the chat. You've opened a bottle of Coke, let's say a big 2-litre bottle of Coke. You've had a glass out of it or Fanta, whatever your poison is. Okay. It could be, I was going to say Prosecco then, but maybe not. So you basically something with fizzing. You've opened it, you've had a glass out of it, you put the lid on, you put it back in the fridge. Does anybody have any tips to keep it fizzy? How do you keep it fizzy? That's what I want to know. So while you put your answers in there, I'm going to carry on talking. So you got a brand new bottle of Coke, okay? Brand new bottle of Coke. And you look at it and you turn it upside down, no bubbles in it. You can't see any bubbles in it at all. Now, the reason is there's an equilibrium there of carbon dioxide. You've got aqueous carbon dioxide, so carbon dioxide dissolved in the liquid, and gaseous carbon dioxide. Right now, the equilibrium is really way over this side, okay? Really far over the side with the aqueous carbon dioxide. So you've got aqueous carbon dioxide and gaseous carbon dioxide, just those two, okay? So that bottle is under high pressure, okay? So what's the equilibrium done? Will it favor the gaseous CO2 or the aqueous CO2 if it's under high pressure? Will it favor the gaseous CO2 or the aqueous CO2 if it's under high pressure? Ooh, split down the middle at the moment. It favors the aqueous. Okay, it favors the aqueous, because remember, the higher the pressure, if you increase the pressure like there is in a bottle of Coke, it favors the side with the fewest moles of gas. The side with the fewest moles of gas is the side with, well, no moles of gas. It's just the aqueous side. Okay, so under high pressure, all of that CO2 is in the equilibrium on the right-hand side here, or your left-hand side, whichever way you're looking at it, in aqueous. Okay, so we got, in fact, let me just show you. I'll show you the equilibrium. Hang on. So CO2 aqueous and CO2 gas. Now under high pressure, oh, hasn't done it. He's still looking at my head. Okay, there it is. So under high pressure, we're favoring this side because a high pressure favors a side with the fewest moles of gas, and that is actually this side. All right, so favors the side with the fewest moles of gas, and that is high pressure. So that's why you can't see any bubbles in your Coke when you got a brand new bottle, okay? As soon as you open that lid, what happens? You've decreased the pressure. Which way is the equilibrium going to shift if you decrease the pressure? You've opened the lid, all that pressure escapes, pressure goes down, it's going to shift to the right. And all of this aqueous gets turned into gas. And that's why you see bubbles just magically appear inside the Coke, okay? So that's why that you get that shift in equilibrium, okay? Good, yeah, it turns into a gas, so it favors the side with more gas. So of course, that's why, unless you put the lid back on, it's trying to increase the pressure and find a new equilibrium. If you leave the lid off, is it ever going to find an equilibrium? No, because it's constantly trying to produce more CO2 gas. But then instead of building the pressure up, it's just escaping through the top of the bottle. And that's why it goes flat really, really quickly unless you put the lid on. Okay. Yeah, it is pressure. We're talking about pressure, Miss C. Absolutely. Okay, so the pressure in the bottle to start with is really high. You take the lid off, it lowers the pressure. What the equilibrium does is shift to the right to favor the side with the gaseous CO2, trying to increase the pressure again to maintain the equilibrium. but it can't do it because all that gas it produces just escapes into the atmosphere. It's not a closed system. Okay. Yeah, absolutely, Benyon. All right. So next time you open a bottle of Coke, you'll know, won't you? So best thing to do is, if you can, just try and increase the pressure. You can actually get, if you're sad enough, little pumps. So you put a pump on the top of the bottle, you can pump it up and make sure that it's under high pressure, just air in that bottle, and that will keep it fizzy for longer. Okay. Some people squeeze all the air out of the bottle so the Coke reaches the top. That's the worst thing you can do, because then it's got even more space to try and fill up with gas and it goes flatter quickly. Okay. Yeah, if you're sad enough. You know what? Chemistry geek. I'm a chemistry geek. I'm a science geek. You know what? I think the majority of the human population look at us as a little bit sad, but you know what? We make the world go round, right? So yes, increasing pressure will favor the left-hand side here. So that's what I was saying. If you pump the bottle up, so once you're taking the lid off, you're going to pump, you pump all that air in and seal it off under high pressure. It will stay fizzy for a lot longer. Okay. I've heard some people put in like a spoon in it, like dangling the handle of a spoon in it. I'm like, no, like, what's the reason for that? That's crazy. Anyway, I'm rambling. We need to move on. So let's get rid of this. And let's talk about temp, baby. And what color am I going to use? Let's go blue. Okay, so temperature. Make memes because it's April Fool's Day tomorrow. It is April Fool's Day tomorrow. You're right there. Maybe I should. Maybe I should tell everybody to put a spoon in their Coke. Miss C, you're absolutely right. So an increase in temperature. If you increase the temperature, what's it going to try and do? It's going to try and decrease the temperature. The only way it can do that is by absorbing heat energy from the surroundings. And we did this, okay? We've talked about exo and endothermic reactions. So an increase in temperature favors the endothermic reaction. Why? Because it absorbs heat energy from surroundings. Okay, so that's how it does it. Remember, the only thing your equilibrium can do is actually move to the left and move to the right. So an increase in temperature favors the endothermic reaction, which makes sense. We've increased the temperature. Equilibrium is like, no, 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 no. I want to bring that temperature back down. How's it going to do that? Well, the only way to do it is by favoring the endothermic reaction, which absorbs energy from the heat surroundings, from the surroundings, and draws it in as chemical energy. Okay, so of course, decreasing the temperature favors the exothermic reaction. Oh, it's nice, it's cold. We need to raise the temperature back up. How am I going to do that? Well, I'll favor the reaction that releases heat energy and warms it back up again. Okay. So do we need to know why this happens? No, you just need to be able to explain what happens when you get a change in conditions. That's all we need to know, Emily, okay? So of course, in order to answer these questions on temperature, you need to know one thing. Usually they will put on the end here, so delta H equals, I don't know, plus 90 kilojoules per mole. So what does that denote? Well, that little delta H on the end of the reaction, that denotes the enthalpy change for the forward reaction, So the forward reaction here is endothermic, the reverse is exothermic, equal and opposite, just like in Hess's law, okay, whereby we were flipping the arrows, weren't we, yesterday? So if it's plus 90 one direction, it's minus 90 the other. So just that one bit of information on the end there can tell you, that's all you need to know. The forward reaction is endothermic, the reverse reaction is exothermic. Okay, so that's our Le Chateliers in a nutshell. Now, the last thing I want to mention here is catalysts. Catalysts do not affect the position of equilibrium. Okay, they do not affect the position of equilibrium. The reason is that they are not a changing condition. What they do is lower the activation energy for a reaction. Now, if you've got this reaction here, okay, so the forward reaction is actually, so these are our reactants, these are our products, and this is the catalyst. It not only reduces the activation energy for the forward reaction, but it reduces the activation energy for the reverse reaction. So it treats them both equally. What happens is when you add a catalyst, it just reaches equilibrium more quickly. Okay, so where you've got you know, your, let's say your product is increasing and your reactants are decreasing. Okay, so this is the concentrations of reactants and products, and it may be at this point here we reach equilibrium. Okay, so we had 0 products to start with, and here's all our reactants. As they get used up and they reach an equilibrium. If you added a catalyst, what will happen is you just reach equilibrium more quickly. So here is where you reach equilibrium with a catalyst. Okay. So in the content guide, okay, I will unlock the lectures. In fact, it just ran away with me yesterday. I'll unlock the lectures for this for you guys to have a look at. Okay, these graphs are really handy in terms of, you know, showing what happens in terms of catalyst and equilibria and where equilibria lie and stuff. Okay. Right, we need to finish up, guys. So we do need to talk about Kc. All right. So Kc. This is the equilibrium constant with respect to concentration. Okay, so they'll only ever ask you to do this with the concentrations of reactants and products, okay, which is really, really important. So let's use this Haber process again. Why not? N2, 3H2, 2NH3. Okay, so the equilibrium constant here, there's the expression is your first port of call. Okay, your expression is your first port of call. So Kc now equals the concentration of your products, which is NH3, over the concentration of your reactants, and you need to multiply them up. Okay, oops, like so. What's missing here? Raseb, yes.
Missing You is a 2016 drama starring Ye Hong-an, Hong Pa-kim and Song Yo-kim. A little girl who lost her father to a serial killer 15 years ago awaits for his release, while a suspecting detective follows the killer upon release. Its runtime is 1 hour, 48 minutes. It has an IMDb rating of 6.6 out of 10 and is rated 18.
It just won't shut up. There we go. That was the virtual assistant, which shall not be named because I've just set her off. So I've learned about a 2016 period drama. It does seem like it's a South Korean one. There we go. Where were we? So we've accounted for the concentrations of our reactants and products. Products on the top, reactants underneath. We do need to account for the stoichiometry here. So that's why it's to the power of, okay? So it's NH3 squared, okay? Yeah, I love that, Grace. Okay, so NH3 squared over concentration of N2 times the concentration of H2 cubed, okay? Cubed. Oh, whoa, whoa, hang on, Aisha, hang on, Aisha. So what we've got here is an expression. Now, of course, what we need to do is find some numbers to go in this expression. So I'm going to move this up here, actually. Okay, so if I said, and this is the way I always write this out when I'm answering questions on this. Initially, let's say we had 10 moles of nitrogen and, I don't know, 30 moles of hydrogen. Okay, and we've got no NH3 to start with. Remember, initially, you haven't got any products whatsoever. It was left to reach equilibrium at a constant pressure and temperature, at which point we only had, let's say, 2 moles of nitrogen left. All right. Now, this is where the stoichiometry can be a little tricky. This is the typical type of question they tell you. This is how much we got put in the first place. This is how much. They give you one thing, one number of moles at equilibrium. Okay, so let's do this in red. So how do we figure out how much hydrogen and how much ammonia we've got at equilibrium? Well, we've got this to go on. Here we've used 8 moles of nitrogen. So how many moles of hydrogen did we use? The question I'm asking, ladies and gentlemen, is how much, what number of moles of hydrogen got used if we used 8 moles of nitrogen? Good, Miss C, 24, because this is a 1 to 3 reaction. For every 1 mole of nitrogen, needs to react with 3 moles of hydrogen. Okay, so this is 30 minus 24. So therefore, we have 6 moles of hydrogen left. Okay, so that's our number of moles of hydrogen left at equilibrium. What about our number of moles of NH3? Well, this is a 1 to 2 reaction. So the easiest thing to do here would be, okay, I've used 8 moles of nitrogen. Brilliant, you guys are ahead of me, 16. So therefore, Kc equals 16 squared over 2 multiplied by 6 cubed, and that will give you your value for Kc, whatever the answer is to that. Okay, I'm sure we can put that in our calculators. So it's a really straightforward thing to do. It's just the bit that students like lose marks on the most is this stoichiometry bit. So it does take practice. Deducing amounts at equilibrium is a really, really key part in this. Okay, so Kc, K is the equilibrium constant. Okay, so it gives a value to the where the equilibrium lies. Now, this is the next thing I'm going to ask you. Okay, so it's the equilibrium constant with respect to concentration, Kc. Okay. Oh, thank you, Louis, 0.593. Now, question. Why is it 16 for NH3? Well, because we've used 8 moles of nitrogen here. Okay. And 1 mole of nitrogen goes in, we get 2 moles of ammonia. So if 8 moles of nitrogen went in, we get 16 moles of ammonia. Okay. So question, 0.593, regardless of what the units are, what does that tell you about the position of the equilibrium? Where is this equilibrium lying? I'll give you 3 choices. To the left, it's directly in the middle, or it lies to the right. No worries, Dennis. Miss C's dancing by the looks of it, to the right, to the left, give it a bit of a shimmy and a shake, spin around in the middle, slightly to the right, slightly to the right, slightly to the right. Okay. Miss C, final answer? Yeah. Okay. So this number here, okay, and this number here. To get this answer, this is obviously bigger than this one. Okay, so the amount of moles we've got in terms of our reactants is bigger than the number of moles of products. That's why this number is below 1. So we've got 1, our equilibrium is right in the middle. If it is below 1, then it lies to the left-hand side, because obviously this number at the bottom here is bigger than the number at the top. So therefore, we've got more reactants than we have products, okay? If it lies to if it's above 1, then it lies to the right, because what that means is that the top number is bigger than the bottom number. Okay, in other words, you've got more products than you have reactants. Okay, there you go. So the position of the equilibrium, we've quantified the position of the equilibrium. Okay, so 0. anything or anything times 10 to the minus whatever, it lies really, really far to the left-hand side. Anything that's above 1, it lies to the right-hand side. If you get an answer of 1, then your equilibrium lies directly in the middle. Yeah, I'm glad you agree, guys. I'm loving the fact that a few of you guys are like, right, okay, I get it, which is great. Okay, that's what we're here for, right? So these are, I'm not going to do units because not everyone has to do units. Okay. Wait, what lies in 1 and why? So if it's 1, if the top number and the bottom number, so your number of moles of products and your number of moles of reactants are the same. So like 10 divided by 10, well, it's 1, isn't it? So that means your equilibrium lies directly in the middle. Okay. That's why 1.0 is directly in the middle. Okay. Now, I will just drop this in, actually. Somebody mentioned it just before. The only thing that can affect KC is temperature. Now, the reasons why and the reasons why the others don't is a whole other 45-minute session, okay, guys? So the units, yes, okay, the units, all you need to do is just replace all of these with moles per decimeter cubed, okay? So this would be moles per decimeter cubed squared divided by moles per decimeter cubed times moles per decimeter cubed. All right, and you just have to cancel them out, okay? Absolutely, Emily. That is exactly what it does. It quantifies the position of the equilibrium, okay? Now, which way will temperature affect Kc? Well, what you need to do, and this is definitely the last thing I'm going to say, if you have got, let's get rid of this, bring this back in. No, bring this back in. Down here. Let's say, in fact, I know this is plus 90. Okay, so this is a typical question. If we've got a forward reaction, which is endothermic. If I decrease the temperature, okay, which way is the equilibrium going to shift? If I decrease the temperature, which way is this equilibrium going to shift? To the left or to the right? If I decrease the temperature. Good. Yeah, absolutely. It's going to shift it to the left. So by shifting to the left, we are increasing our number of moles of reactants. So reactants increases, and therefore our products decrease. Okay. So in this reaction, I've decreased the temperature. It shifts to the left. Okay, so that means increase in the reactants, decrease in the products. So that means that this number is going to get bigger and this number is going to get smaller. So what's going to happen to the value of Kc if I decrease the temperature in this equilibrium? Good, absolutely. Therefore, Kc decreases. Okay, therefore Kc decreases. All right, does everyone get that? So all you need to do is apply your Le Chatelier's first of all. So if they ask you what happens to the value of Kc if you do this to the temperature. So all you need to do is apply your Le Chatelier's, which we did before. You can see the reactants increases, so this number gets bigger. Products decreases, that number gets smaller. So therefore, it's going to go down. Okay, so that's why Kc decreases, because of the shift in equilibrium. Now, they're not going to ask you why temperature affects Kc and the others don't. They're not going to ask you why. It's handy to understand why. It's good to have a good general feeling about it. I'm pretty sure I talked about it in the live class for this, okay? But I'm not going to do that now. The same is applied for Kp, absolutely, okay? So it is a great way of thinking, right, okay, what happens to Kc, okay? But it's only temperature that affects Kc. So I've seen in an exam, they say a change, if I increase the concentration of ammonia, how does that affect the value for Kc? And the answer is what? If I increase the concentration of ammonia, how does that affect the value for Kc? Kp is next year, okay? Kp is year 2. Good, Raseb, none. Okay, so if you increase the concentration or the pressure, okay, nothing's going to happen to the value of Kc or Kp. Okay, Louis, good question. For the units of Kc, do you have to put the positive power first, or doesn't it matter? In chemistry, doesn't matter. They'll accept either. I tend to stick to, you know, if you've got an inverse power, then I tend to stick to moles minus 1 decimeter 3, for example. It doesn't matter. It really doesn't matter. So, right. Don't forget, guys, make sure, if you haven't already, get the Exambulance course that maps out what we're going to be doing over the next few weeks to help you guys finish. Give us a like. Don't be afraid to give us a like, folks. Let people know get on Instagram. Let people know what you've been doing and what we're doing. Make sure that you're with us tomorrow, okay? And we'll do some more year 12 stuff. What is tomorrow? That is a very good question. I cannot remember from day to day. I'm pretty sure we're doing some kinetics tomorrow, some rates. That's all right, Christine, my pleasure. Aisha, what is the timetable for the topics? Okay, so the timetable is in the Exambulance course. So just go to tailoredtutors.co.uk. You'll see a big white block right on the homepage there. Just log into the Exambulance course, sign up to it. It's absolutely free. And the schedule for all the live classes and stuff is in there, okay? Thank you, Louis. So yeah, please spread the word, guys. I mean, you know, I've got a good number of you in here. Not as many as I'd like. I think, you know, there's definitely more people out there that can benefit from these. Okay. So thanks, Miss C. Kinetics tomorrow, and I will see you then. Thank you very much, guys.